So the first part looks at modeling, trying to describe the features and the dynamics of a network. So we're focusing here on the case that was mentioned yesterday, where you have a fixed number of nodes and there's some dynamics of the interactions. So links are coming and going over time. We're thinking in particular of communication and human social interaction, so maybe emails or Twitters or telephone conversations between a fixed set of users. So that's the context that we're thinking of. I'll talk about a recent model, but this is really using a framework that Pete and I put together a couple of years ago. So just taking a step back, what are we trying to do here? What's the motivation for this, and what are the challenges? Well, we'd like to understand what's causing these dynamics. What makes a new link arise in the network? How do links disappear? If you're given today's network, what laws of motion are telling you something about tomorrow's network? If you have a model, then you can try to calibrate the parameters of the model. And if the model is statistical, then there's a very nice likelihood automatically built into this process. So by comparing likelihoods, you can decide which of the two models or more than two models is most appropriate for the data. And the real reason for doing this is that we can then use that model. We can forecast what's happening in the future, we can make predictions, and we can do what-if simulations. We can do things on a computer that might not be ethical or feasible in real life. Okay, so we can run trials, knock out nodes, intervene with the network in some way, and predict future behavior. So this is the framework that we tend to focus on. It's a discrete time, so time points, think of them as days or hours as we go forward. And it's stochastic, it's a Markov chain. The state space is the set of all possible networks. So today, at time tk, we know the adjacency matrix ak. Let's suppose this is a simple, unweighted, undirected network. So given today's network AK, then there's a probability of every other possible network arising tomorrow. Now, if you try and parameterize that kind of Markov chain, then you find there's lots of parameters involved. So we like to simplify things. And the version that we focused on, we like to talk about in terms of birth and death of edges. So given today's network, if there's an edge in today's network, then there's going to be a probability of that edge remaining or disappearing tomorrow. And that's going to be independent over all the edges. And again, if there's an edge missing in today's network, then there's going to be a probability of that edge appearing in tomorrow's network. Okay, so it's an edge-focused type of modeling. Once you're given today's network, all those events are then independent. So what's a good way of putting together some rules about how edges may arise or disappear over time? And we have various ideas that we've published. I'm going to focus on one particular case, which I think is realistic, and also we can do a little bit of mathematics, so we can actually sort of prove something about it. So the idea here is called triadic closure. This is a very well studied topic in social sciences. The idea that the more friends you have in common with somebody, the more likely you are to become friends with that person. It's a reasonable sort of hypothesis. If you tend to interact with the same circle of friends, then you tend to make that new friendship. Okay? So in terms of what happens to the edges, well, given today's network, we're going to keep the death process simple. So we lose friends at some constant rate. So independently of the network, if the edge is there today, then there's some probability omega that the edge will disappear tomorrow. But here's this triadic closure idea. If there's an edge missing in today's network, then this is the probability. So it's between nodes I and j. This is the probability of that edge arising between nodes I and j on the next day. So there are two parameters here. There's a delta and an epsilon. Delta is just the basal rate, state-independent rate at which we may sort of arbitrarily make new friendships. Epsilon here is the strength of this triadic closure effect. So what we're doing here is raising today's adjacency matrix to the power 2, and as we've heard several times over the last couple of days, that's a way of counting the number of walks of length 2 or paths of length 2 between I and j, or in other words, it's the number of neighbours that I and j have in common, the number of friends that they share. So the more friends I and j share, the bigger this quantity, and epsilon then is the strength that we associate with that triadic closure effect. So it's a relatively simple, although non-linear, model of edge birth over time. We need some constraints on the parameters just to guarantee that this overall probability is between 0 and 1. So it's a Markov chain. I'm going to show you a path of the Markov chain. So the state space is the set of all networks. These are my parameters that I'll use all the way through. So in particular, there's 100 nodes in this network. So here's time increasing in steps of 50 from time 0 up to time 750, and the dots are the edges in the adjacency matrix. My notation here, this is ER stands for Erdos-Renyi, just the usual tossing a coin to put the edge in. That's my initial condition with 0.3 as the probability of an edge. So my starting graph has edges placed uniformly at random with probability 0.3. So it's 30% dense to begin with. If you let time evolve, this is one path through the Markov chain. I don't expect you to spot any patterns there, other than to notice that there's more and more dots appearing. So the blue is increasing, so this is becoming denser over time. And in particular, if you count the edge density at the longest time, 750, then it's around 71%. So out of all the possible edges, about 71% exist after a long time. And that's when I start with a 30% edge density at time 0. So then taking the same model exactly, just changing the initial condition. So now I start with a less dense network of 15% edges. Let time evolve with the same modeling parameters, the same birth and death law. Then this time the edges get less dense, and at this largest time, 750, we now have around 5% of the edges present in the network. Okay, so those are just two independent paths of the Markov chain, starting at two different initial conditions, but with the same modeling parameters. So it's the same model, different initial data. Can we explain why we get these two different types of long-term behavior? Well, the answer is yes, otherwise I wouldn't be showing you these experiments. So we're going to do what we call mean field, and mean field is what physicists say when they don't really understand what they're doing. That's my summary. So here's a statement which we're fairly clear is true. Okay, so let's think about long-term behavior of this Markov chain. Well, it's ergodic. I think that's fairly clear because of the way that the birth and death are defined. There's always some guaranteed non-zero death and non-zero birth probability. That means if you focus on a pair of nodes and look at the connectivity between those two nodes as time goes to infinity, then the frequency with which you see an edge will tend to a constant as time goes to infinity. So let's call that P star. So if you look at this pair of nodes, let time go to infinity, the frequency with which you see the edge will, over time, will converge to some number P star. On the other hand, there's nothing special about any particular pair of nodes. Everything's invariant under relabeling. The dynamics don't depend on the node labeling. So it must be the same P star for every pair of nodes. Okay? So in this long time sense, we must have an Erdos-Renyi type of structure where whatever edge concerns you, that will appear with some fixed probability P star as time goes to infinity. So in this sense, there's an Erdos-Renyi structure in the long time. So taking that through and doing something heuristic now, let's just ask ourselves what would happen if we did have an Erdos-Renyi graph at some time. That would be defined solely by this scalar, pk. This is the probability of seeing an edge between a pair of nodes at time k. So if we just insert this into our model, what's the corresponding value for pk at the next time point, if this really were a sensible thing to do? Okay, so pk is the chance of the edge being there today. What's the chance of an edge being there tomorrow? Well, there are two cases. Either it was there and it didn't die, so 1 minus omega is the chance of it not dying, and pk is the chance of it being there yesterday. On the other hand, maybe it wasn't there and it was born. And if I go back to the model, the birth probability is a constant delta plus epsilon times the number of neighbors that they share. So 1 minus pk is the chance that it didn't exist yesterday. This is our factor describing the chance of a birth. So there's the constant, the basal rate delta. There's the triadic closure strength. And now there are n minus 2 possible neighbors of these two nodes. And the chance of the appropriate pair of edges being there, so that I and j are both connected to those neighbors, is given by pk squared. Okay? So this is our heuristic mean field approximation to the behavior of the adjacency matrix in this model. Okay, so this is a scalar parameter now, pk. It's just the density of the edges. It's a macro parameter that we're trying to extract from this micro scale description. Okay, and it's a trivial non-linear type of iteration. It's a cubic iteration, so you can look for steady states of this, and you find that there are 3 real roots because it's a cubic, and generically there are 3 if you have small parameters. And as you might expect, 2 of them turn out to be stable. That's the dense and the sparse case, and in between them there's an unstable, linearly unstable steady state. Okay, so for the parameters I used for my simulation, the steady states arise where these 2 curves meet, where the cubic meets the linear. I should say these are generated by Peter Grinrod in nice low resolution. At Reading they can't afford many pixels, so these are Pete's pictures.
It costs money.
That's right. Yeah. So this agrees with the simulation. The less dense stable steady state is down at around 5%. The more dense steady state is up at 72%, and the unstable intermediate state is around 23%. Okay? And then just to try to convince you a little bit more, here's a lovely smooth curve in Peter Grinrod style and a jagged curve. The lovely smooth curve is this one, and the jaggedy one is just above it. So what we're doing here is one of these is a micro scale simulation of the Markov chain, which we then extract macro features from. So we simply count the edge density at every point in time for one path of the Markov chain. That's the jaggedy curve. And the lovely smooth curve is just the mean field iteration. The pk plus 1 is a function of pk. And you can see, because we're starting with Erdős-Rényi, which is a little bit of a cheat, but this mean field model very nicely follows the micro scale simulation in terms of capturing this macro feature. Okay, if you didn't start with an Erdős-Rényi, there'd be a little bit of catch-up time, but it would eventually follow the right kind of behavior. And this bistability is really what we think is the interesting part of all this. So what we're doing here is we're starting 5 independent paths from the same initial condition, which we've specially chosen to be close to the unstable fixed point. So there's an unstable fixed point around a 0.23 edge density. We start with exactly the same initial condition, but 5 different independent paths, so different microscale noise. And 4 of these curves decide to follow down to the lower of the stable fixed points. But one of these, because of the microscale detail, has enough impetus to get going and then lead itself up to this richer, denser stable fixed point. Okay, so in a sense we can predict what's going to happen, that we think there are these 2 stable fixed points, but we can't tell you which one is going to show up in a particular simulation. And of course this has some nice implications. If you're a mobile phone company trying to generate customers, or if you're an online social network provider trying to get a nice rich interactive structure among your users, then you want to be up here. And a little bit of work just to help this information to get going will allow the path to head up towards the desired fixed point, and then you leave it alone and it very nicely carries on and self-organizes into that rich state. Whereas if you see this kind of behavior happening, then you know you need to work a lot harder to get the desired behavior. Okay. So that's a little bit about modeling, and I'll just wrap up that half of the talk with a summary and then some observations. So what we're doing here is using a stochastic modeling framework, focusing on the idea that edges can be born or can die from one time point to the next. And we tried to build in this law of motion based on triadic closure. So the more friends two people have in common, the more likely they are to build a friendship at the next time point. And we have this mean field analysis, which seems to do a good job of predicting the behavior of the model, at least that particular macro scale feature. There are many things that can be done, and some of these we're working on, in particular calibrating the model to some real data. And because it's a stochastic model, as I said, it has a likelihood, so it's not particularly difficult to see how you might calibrate that model. Also, it's nested in the sense that epsilon equals to 0 is just completely Erdos-Renyi type behavior, so you can do a nested comparison and see whether epsilon equals to 0 is more realistic than epsilon greater than 0 on some data sets. So you can test in a statistical manner for whether you're seeing triadic closure in the dynamics. We're doing discrete time, and there are some interesting issues which I'll talk about later with anybody who's interested, about trying to generalize this modeling framework to the case of continuous time. It's by no means obvious what to do in continuous time. And we'd like to also analyze processes on this dynamic network, put an SI model, SIR model on top of that evolving network. And we have a little bit of work in this direction. Okay, so maybe I'll stop there for any questions on the first half if anybody wants to chip in. Yep, sure.
I haven't seen this mean field approach, but I think what you're saying is that you start with whatever you start with, and then relationships evolve. But you're going to say that as a gross approximation, you're just going to see, as time goes to infinity, how many people are left, and then assume that everything is independent to make a calculation.
How many edges are left? Yep.
How many edges are left?
Yep. Yep.
Make a calculation, and then say, okay, in that calculation, here is what I get. I get 3 points, 2 of them are stable. So I'm guessing that what will happen in the true limit is something like that. Is that
well? Well, there's one thing I said this is heuristic. I was expecting a different kind of question. On the one hand, I said this is ergodic. On the other hand, I tried to convince you that there are two stable steady states, and that those things don't go together. Okay, so there can't possibly mathematically be these two, delta functions, both being the invariant measure. So I guess this is metastability that we're observing, and in the very, very long time, you'd maybe see some mixture of those two stable steady states dominating the behavior. Does that answer your question?
I actually hadn't gotten to my question.
Right,
how
okay.
close is the mean field theory approximation to?
Well, in practice, it seems to work. We haven't got a proof, and I'm not sure that you could. Well, you can't because it's ergodic, and we're trying to claim there are two measures. So that's why we didn't try and make it rigorous, because it can't possibly be rigorous. But if you look at the arguments, that I think as an approximation, they do seem to be reasonable.
And do people try to make some sort of rigorous framework?
Well, if you think about it, near the threshold point, the mean field is deterministic. It's just a deterministic iteration, so that can never be correct. Where the fine details of the stochastics actually matter. So anywhere where you're near an unstable point, what does near mean? But anyway, anywhere where you're very close to a stable point, clearly it's going to fail down. Similarly, anywhere where you're in a network which is particularly sparse, and say the triadic closures are formed, it's going to kind of fall down because the mere details. Suppose you had a network that had no delta, had delta is 0. Then the only means of making friends is to make friends with people who are already friends of friends. So if we start off split into two groups, Brazilians and British people, then because none of us know each other, we'll never make friends. Right? Whereas in the mean field, they would eventually, because you smooth some things out. So actually, there are cases when, but actually just putting delta back in kind of rescues the situation. But in general, anywhere where the stochastic details of the actual networks matter, the actual initial conditions, or you're close to an unstable point, actually it can only be a wish thing.
Yeah, and I think any sort of proof would have to be really complicated, involving metastability and transient. So it's not the kind of thing we'd like to get into.
Are there conjectures that are formulated even in some sort of rigorous sense?
No.
No? Feel free to. No.
This mathematical theory of birthday processes, I don't know how much. I know that they look at stability.
Yeah.
We stole this idea
It's solved in a one-dimensional case, but of course it's not a one-dimensional case.
Yeah.
We sort of stole this idea from mathematical biology to get going.
Yeah. Yeah, sorry, Mark. Yeah.
How stable is this result when because here you had a square.
Yeah.
So you could imagine, to add something, I don't know, a cube maybe, or something, or
No,
stable or transition.
We discussed this, but we haven't tried it. But we think the heuristics are much less valid in the case of higher powers of A. If you think of the independence assumption, it's very neat the way this p squared comes in. What's the chance of the two neighbours both being connected to the right nodes? If you start raising powers, you can write down the mean field model, but we don't think it's as useful.
But the
But
simulation
we haven't tried that yet. We haven't tried it, but we just think it's interesting, but we think it's not so valid as this. Yeah.
Maybe if the mean field is correct or not, that's a
Yeah.
question.
Sure. Yeah.
Is the existence of this transition robust to,
Yeah.
to more details
Sure.
or some other
Yeah.
thing? That's
Yeah.
would be nice to check.
Yeah.
By simulation.
Yeah. Sure. Okay, so I'll press on. So the second part of the talk is the opposite. It's data-driven, trying to extract things from some networks. This builds on some work with Ernesto and Pete, and Mark Parsons is a student at Reading. And this goes back to this idea of walk counting, and the original paper I'm aware of is Leo Katz from 1953, where he used walks to measure centrality. So now we're thinking of time-dependent networks and which nodes are important and how can messages be passed around. So suppose you have this kind of structure on 3 days. Imagine these as being undirected. Then if you look at how A might communicate with C, on time 1 A can communicate with G, and then at time 2 G can talk to C. But there's no way that C can talk to A with that structure. Okay, so there's a lack of symmetry, even though each network is symmetric. Times arrow introduces this lack of symmetry. So you have to be careful what you mean by communication. But as Mark said yesterday, there's a fairly obvious idea of walking around. You can just use the edges that are available, and then at the next time point you can use more edges. So you can, in this notation where we have TK are the time points and the corresponding adjacency matrices, you can define a dynamic walk. The length is the number of edges that you go across. So you need a sequence of time points and a sequence of edges that take you between the nodes, and the edges have to exist at the appropriate times. So it's a perfectly natural concept. We allow the same time to be used by more than one edge. So you can traverse 2 or 3 edges on one day and then go ahead and take as many edges as you like on the next day. That's the way we've defined it. Okay. So the Katz centrality is based on powering up the matrix to count walks, and it turns out there's a very similar concept in this dynamic setting. If you multiply together the adjacency matrices at possibly different time points, then that simply combinatorically counts the walks that take place using edges, on the appropriate time points. So this product with some arbitrary set of time points has an ijth element that counts how many walks there are from I to j from factors, so using W edges, where the corresponding edges exist at those time points. Okay? So we'd like to look at all the possible ways to walk between I and j respecting this time ordering. So we'd like to keep track of all these kinds of walks here. So we'd like a term like this, where you take a step on day 0 and a step on day 1, and we'll use that Katz-style downweighting, the resolvent style, where we multiply by alpha squared if there are 2 edges. Here's a term which takes a step on day 0, a step on day 2, day 3, and then day 7, and because there are 4 edges, we downweight by alpha to the 4. This one takes 2 steps on day 3 and then 1 step on day 9, and that has an alpha cubed. So we'd like all the possible terms of that form where you have non-increasing time indices and a corresponding power of alpha that matches the number of edges. Okay? So we'd like to put all those terms together, which might sound combinatorically difficult, but it turns out all you have to do is multiply together the matrix resolvents, okay, in the appropriate order. So this is generalizing the Katz resolvent into time-dependent networks. Call this matrix Q, and then the ijth entry in Q summarizes how well I can pass messages or communicate with J over that time-dependent data. So you can sum along the rows to see how well node n is communicating with all the other nodes in the network, and you can sum down the columns to see how well node n is receiving information from all the nodes in the network. So we call this the broadcast and the receive communicability. So it's like a centrality measure in terms of broadcasting, and then one in terms of receiving. It generalizes Katz. If you have 1 time point, it reduces to Katz. It's relatively cheap to do because those matrix resolvents involve sparse matrices. So it's a sparse matrix solve at each time point. And the fact that dynamic walks are not symmetric is really mirrored in the fact that matrix multiplication is not commutative. So if you change the order of the time points, you certainly change these centrality measures. So we are respecting the order of the time. So here's an example. This is from some other work with a postdoc, Alex Mantzaris, where we have another model that I haven't got time to talk about. Okay. This is the Enron data set, 150 people or so. Each point here is a person. On the horizontal axis, we just look at their total degree, how many emails they churned out. On this axis, we look at their broadcast centrality. So this is what we think is a better measure of how well they can get out information across the network. So there are a couple of people here who stand out as having high broadcast without a particularly high bandwidth. And it turns out this is the vice president and an executive of the company. Whereas there are 3 people out here who are working very hard, sending out lots of messages, but in terms of the broadcast centrality, not doing particularly well. And 2 of these people were traders, and 1 is unknown in terms of their job. Okay, so this is certainly different. This broadcast centrality is different to simply counting how many messages, how many edges somebody has. It's about the timing of the edges and the follow-on effect. Once you've sent your message, who else is passing it on? That's what this is trying to capture. So just briefly, we have a new version of this which allows for time downweighting. The previous version treats all the walks over the whole time period as being equally important, and we only discount according to length, the number of edges. Well, you can also discount according to time. So if it's a very old message that started a long time ago, then you might want to downweight it by its age. So by updating this iteration in this way, where we introduce this scaling factor, where delta t is the interval of time between one day or one time point and the next, then this matrix SK again is combinatorically counting all the walks between I and j. But as before, we scale a walk of length w in terms of edges by alpha to the w, but we also now scale a walk that's t units old by e to the minus bt. And so this updates both the edge weighting and also the time weighting. So this parameter b goes from 0 to infinity. 0 is the previous algorithm, and infinity is just focusing on one day at a time and forgetting all the previous information. So just briefly to show you that B might be useful, this is a synthetic test using real data. The Enron data again. This is a bit like link prediction, but we're now doing centrality prediction. So we're trying to predict tomorrow's Katz centrality of that network using today's information, any information today or earlier. We look at the correlation between our prediction for centrality and the true Katz centrality on the next day. We sum those correlations over all the time points. So a bigger number means we're doing better at predicting tomorrow's centrality. And what I'm showing here is how that varies as a function of B. So B equals 0 means we're using all the previous information and counting it equally. B equals infinity, or in this case 3, means that we're just using today's network to try and predict tomorrow's network. Okay? And you can see there's some intermediate here around 0.3 where we do a better job. So by using old information but not giving it the same weight as current information, then we can get a better prediction both in the sense of broadcasting and receiving. So just to finish up, what we think is new here is formalizing a dynamic walk and using it to generalize the Katz centrality and pointing out that this gives you new information. There are some people who seem to punch above their weight. Their bandwidth is relatively low, but they can get messages out across the network efficiently. We'd like to do this for weighted edges. We're interested in doing this for very large scale computations, so the linear algebra aspect and the computational side is important. This can be done in real time in principle, so we can categorize networks and then monitor what's happening and maybe flag some kind of warning if the network seems to have changed. Look at who's peaking, who's trending, who's going up or down in terms of their centrality measures, and maybe intervene at the appropriate places. Okay, so I'll finish there, and just thanks to various funding agencies. Okay, thank you. Yep.
I was intrigued because say you can use likelihood to test
yep.
hypothesis,
Yeah.
which is brilliant. But if I just give you a network, just a snapshot of the network, and I don't tell you how many time steps there were involved, how easy is it to do the likelihood estimation?
If it's only one time point, then it's not really feasible. If you have a number of time points, then we just have to assume that is the discrete time interval between network samples. And that's what we're doing essentially. The Enron email data is real-time email, and we tend to summarize it in terms of days or hours or weeks. So that's the level at which we're doing things. So if there's more than 10 data points, time points, that's the kind of thing that we're doing at the moment. Yeah, Mark?
The result is very nice, but how could you expect to, how can you extract some useful information from it? Because it's a complicated object, let's say, and so what do you have in mind? To compute it completely, or to...
Sorry, what is this?
The Q...
Right, yeah. Well, it's really...
the Q, the product of...
So this is, once you take this sum, this is Q times a vector of 1s. So it's just a vector. So if you multiply...
This quantity, for example.
So in general, it's this times a vector that we're trying to find. So inverting a matrix times a vector, that's solving a linear system. And this is a sparse matrix. So it's one sparse matrix solve per time step, which is feasible. This compared to what Google does.
It should contain all information, if I understood well. It should contain all information about all possible paths in this.
Yes, summarized by this weighting factor. Yeah.
So in principle, you could extract many things now from this quantity.
Yeah.
Well, yeah, but it's still pairwise. It's still whatever I and j. It's one summary of how I and j are communicating. Yeah.
Yes.
So you could cluster that, and you could look at the way communities evolve over time. That's one possibility. we think is exciting. Yeah. Yeah.
Yes, no, I think there are many quantities that you could extract.
So it's just
is to define them.
In a sense, this is the best. We think, this is a good static summary of of what's gone on so far. This is like a weighted network at time k, telling you what's happened so far. That's one way of describing it.
What would be the typical complexity of this calculation? I mean, to compute this quantity?
Well, solving a linear system, it's roughly order n. If there's only a fixed number of edges per node, then it scales like order n. And you can always just replace this.
Times m or not?
Yeah. Oh yeah. So for every day, n per day. Yeah. But also you can approximate. You can approximate this by 1 plus alpha a, and then it's just a matrix multiplication. So that is really order n per day.
We solve it in particular. There are numerical analysis by Bensi and Boyd. They use the quadrature rule methods, and they solve this in a very efficient way. So they have developed now a program so you can do in seconds or something like that for 100,000 nodes in a laptop.
Okay, so standing on the shoulders of giants.
Yeah. So it's published in Linear Algebra and this application in 2010 by Bensi and Boyd.
So we had a guy from Telenor saying they can just about over the weekend multiply their matrix by a vector, of all their employees, all their customers. So they're quite happy to think about this kind of computation. What they can't do is compute an eigenvector of the adjacency matrix. That would be just too unthinkable. But they can multiply the matrix into a vector.